The last two speakers will be Professor Jinzhu and Professor Li Wei. They will talk about the topics on causal attribution, which is a rising area in causal inference and is very important for artificial intelligence and machine learning. And let me first introduce Professor Jinzhu. Professor Jia is a researcher and doctoral supervisor at the School of Public Health, Peking University. He obtained a PhD degree from Peking University in 2009, and then did postdoc research at UC Berkeley, and then worked in the Department of Probability and Statistics, Peking University. He joined the School of Public Health of Peking University in 2018. His research interests include high-dimensional statistical inference, big data analysis, machine learning, causal inference, biological statistics, and so on. Okay, now let's welcome Professor Jianing to give the talk, evaluating causes of effects by posterior effects of causes.
Okay, today I'm going to talk about evaluating causes of effects by posterior effects of causes. This is a joint work with Zhitong Lu, Professor Zhi Geng, Professor Li Wei, and Zhu Shengyu. So in the conference, we have already learned a lot of about effects of causes, and so today in my talk, I'm going to talk about something different. It is about causes of effects, and I will talk a little bit about the previous measurements about the causes of effects in literature. Say the probability of necessity proposed by previously, and I will define a new measure about the posterior effects of causes and compare the new measurements with a probability of necessity. Okay, for the effects of causes, we already know that it can be defined as the expectation of the potential outcomes of y1 minus y0, where the y1 means the outcome in the treatment group, and the y0 is the measurements in the control group. And it is about inference for the potential outcomes or the counterfactual inference. So usually when we try to estimate the causal effect, we use the random clinical trials, or in some observational studies, we can also estimate the causal effect. But in the observational studies, we usually have to have some assumptions, like we observe all the confounders, or if there are some unknown confounders, we have to use some technology like instrumental variables, or some new developed methods. Okay, here is an example about medical diagnosis. Say very interesting about how to tell the reason about a person's disease, the blood pressure. We know that one patient has a high blood pressure, but we want to know what is the reason. So it is about the attribution. So a lot of designs can be used to estimate the causal effects between the variables, like the 5 possible risk factors about the exercise, the diet, the heartburn, the heart disease, or chest pain. So after we collect the data, we can have all of the distributions shown in the table. So after that, we can calculate the causal effects. So here, this is an example I will show you later. After we calculate the causal effects, can we see that if the causal effect is bigger, then we attribute the outcome of the high blood pressure to the one with the highest causal effects? I think the answer is no. Okay, before we answer the question, now let me give a few brief introduction on the notations. Here we are interested in the binary causes. X is used to denote the binary causes, and Y is the binary effect. And we use a traditional notation about the causal effect, causal inference. Yx equal to 1 and Yx equal to 0 to denote the potential outcomes. Okay, if there is only one single cause, previously Dawid, Figman, and Finberg defined the probability of causation to do the attribution. So the probability of causation is denoted by the PC. It is a probability of Yx equal to 0 given this quantity. So it means that if one person receives the treatment and he obtains an outcome under this condition. So what if he does not receive the treatment, and what is the probability that he does not have the outcome? So there is another measure to define the attribution. It is called the probability of necessary causation. So it means that conditional on the population that everyone receives the treatment and they develops the outcome. So what is the probability of the outcome to be absent if those people receives no treatment? So these two definitions are different, but if there is no confounding between the treatment and the outcome, then they are equal. And also there is another measurement about attribution called probability of sufficient causation. And they have the relationship. We see that the PS probability of sufficient causation is equal to PN if we change the treatment from X equal to 1 to 0, and we also change the outcome from Y to 0 to Y equal to 1. Okay, so well, what is the property of this probability? The probability of PN, this is a definition we already introduced in the previous slide. It is a counterfactual quantity. You see here, when we define the probability, we define it as a potential outcome. So generally, it is not identifiable. So to make it identifiable, we need a few assumptions. The first one is about monotonicity. It means that if one receives treatment, then he will have a higher outcome, bigger outcome. Another one is about there is no confounding. So if there are some unmeasured confounding, then there is a problem. Even in the causal inference, when you try to estimate the causal effect, you better have the no confounding, no unmeasured confounding. If you have that, you have to have some use some other technique like the instrument variable. So for here, for simplicity, we first assume that there is no confounding. Okay, under these two assumptions, we can show that this probability of necessity equals to this quantity. The denominator is the probability of Y equals to 1 given X to 1, and the numerator is a causal inference, the causal effect, right? It is also equal to 1 minus 1 over the RR. RR is a relative risk used in epidemiology. So here we define a new measurement. We see that after we see the evidence, so we see that the person has developed some disease or some phenomenon, like the person has the high blood pressure, and we see some evidence, we see some status of disease. And after we have the evidence, we want to calculate the causal inference. So if the person have some disease like x equals 1, then what is the difference between the outcomes if he did not have the disease? So this quantity measures the causal effect of x on y in the population of cases only, okay, with exposure x equal to the observation. So this is different with the traditional average causal effect. So the traditional average causal effect measures the causal effect for population of both the cases and the controls. So this is the very different one here. When we try to have the total causal effect, we only conditional on the population of cases. So here we can show that the new measurement is equal to the previously defined quantity Pn if there is only one single exposure. But in reality, usually we have a lot of causes, like in the example I have shown in the previous slides. When have the outcome y is equal to y denotes the high blood pressure, and we have 5 potential causes. So for multiple potential causes, there is another quantity called AR, the attributable risk. It is a population attributable risk. It is defined as this quantity. So from this quantity, we see that it measures the proportion amount by which a disease risk will be reduced if all the risk factors, here you see that x1 equal to 0, x2 equal to 0, xp equal to 0. So if all the risk factors were eliminated from a population, so what is the proportion that a disease risk could be reduced? So this is the attributable risk. So this attributable risk does not measure a single attribution. So if we want to see how we can attribute the outcome to one single risk, we can use another quantity called adjusted attributable risk. So here we sum over all of the other risks. But for this definition, we see that this set x minus k cannot obtain any intermediate factor on the causal path from k to the outcome. So for multi-causes, we also have the same definition for the total causal effect. It is defined as the average causal effect of the y on x, given the evidence that we have the outcome y is equal to 1 and the exposures. And because there are a lot of potential causes, we can also define the direct causal effect on this population. And it is just the like the traditional direct causal effect by controlling all of the causes on the causal path, but we have to have this definition given on this special population. Okay, after we have the definition about the posterior causal effects, we now have studied the property of this quantity. The first question is that if this quantity is identifiable or not. So here we also have these two assumptions, like the identifiability of the probability of necessity. The first one is about no confounding. Okay, because there is only one cause in the previous studies, so previous assumption about no confounding just says that there is no confounding between X and Y. But here we have a lot of causes, and the causes are related with each other. So we say that there is no confounding between X and Y. Also, there is no confounding between the X. Another assumption is about the monotonicity about the on the relationship between X and Y, also between X and its effect, because causes also affect each other. So the relationship between each pair of the causes and effects also satisfies the monotonicity assumption. So after these two assumptions, we can show that the quantity we defined can be identified. Also, here we see that when we define the no confounding and the monotonicity assumptions, we have to specify between the causes or the exposures. But we know that in causal relationship, causal system, the order usually is not unique. So, but we can have a property like this. It says that if two different topology orders satisfy the assumption, these two assumptions, we can see that if anyone satisfy the assumption, then the other one also satisfy the assumption. So it says that the quantity we defined will not be affected by the topological order you defined. Okay, now this is the result. It says that under the no confounding assumption and the monotonicity assumption, we can estimate the potential the counterfactual probability given the evidence after we remove the exposure. Then what is the probability of the outcome to be 1? And if we can calculate this probability, then we can estimate the posterior total causal effect, and also we can estimate the posterior direct causal effect. Okay, in reality, sometimes you do have the whole causal relationship or the whole causal system, but you can only observe a few factors or a few exposures. So if you observe only a subset of this potential causes, then we can also estimate the posterior total causal effect given what you have observed. It is just the sum of the sum of the whole posterior total causal effects times some probability and some of the unobserved factors, just like the marginal probability, and just like the relationship between marginal probability and the marginal and joint distribution. Okay, we can also link the new developed measure with one previous defined like the AR, the conditional AR. We prove that the posterior total causal effects of one cause on the outcome, given only the outcome without any other causal variables. So this quantity is equal to the AR defined previously. Okay, finally, let's see one example that we can show how usefulness is the new developed measurements. This is an example I mentioned before in the beginning of the talk. So this is the causal system between the 5 potential causes and the outcome. And with observations, we can estimate the probability, the conditional probabilities. And with this conditional probability, we can have the joint probability. So after we have the probabilities, we can estimate the causal effects or the PN, the post TCE or something. So here for the evidence of this X, we see for one person, he has blood pressure with Y is equal to 1 and all of the potential causes X equal to 1. So now how can we tell what is the reason for the person to have this high blood pressure? So if we use a PN defined by Pearl to measure the probability of necessity, we see the biggest probability is X4. So probability we will attribute the the effect of Y equals to 1 to this factor. And if we use the other measurements like the posterior TCE, we can also see that this X4 is the biggest. Now it seems that this new one does not gain much more. But if we have another example, like here, this is the same. It is the same causal system, but for another person, we see that this X has no exposure on X4. It means that it has no heart disease. And if we still use this PN to calculate the probability of necessity, we see that we have the biggest one as X5. So it means that if we use this probability to attribute the effect of high blood pressure, then we see that we probably attribute this effect as the effect of X5. But from this DAG, we see that it is impossible, right? Because this one does not affect this Y, right? So if we use posterior total causal effects, we see that we can have the right attribution as X1 is the cause of this effect. Okay, this is my talk. This is a reference. The first one is the paper evaluating causes of effects by posterior effects of causes, just accepted by biometric, and these are some previous literatures. Okay, thank you very much.
Thank you, Jinzhu, for the nice talk. So, I have a question about the causal attribution, the probability of causal necessity.
Sure.
So, this concept depends on the potential outcome of Y1 and Y0.
Yeah.
So somehow I think this may be related to the principal stratification or principal causal effects. So.
Okay. This is a very good question and a very good connection, but I think they are quite different. The most differences is that here, when we try to we will try to evaluate the causes of effects, we know that the outcome is Y is equal to 1. So here, when you try to evaluate the causal effects, you know the effect. But in principal stratification, you only stratify the data according to the potential outcomes without any information about the Y's, right?
Yeah.
Yeah, this is the biggest difference.
Okay. Thank you.
Okay, thanks.
Okay, we can also take one question from the other audience.